Section 6.1 talks about angle measure. We define what an angle is. An angle is formed by two rays sharing a common vertex. So this is ray 1 or ray 2, it doesn't matter. It doesn't specify. So when we say the angle is formed by two rays, we're talking about the angle. But somebody might say, wait, why isn't it this the angle? Well, of course they're correct. It doesn't specify. We call one ray the initial side and the other ray the terminal side. So you could say this is the initial and this is the terminal. And of course somebody might say, wait a minute, I want that to be the terminal and this to be the initial, and that's fine. And how chaotic this is, if I say sketch a graph of 25 degrees, well, all what you have to do is make sure that two rays share a common vertex, and you could say that's 25 degrees. Somebody else might come in and say, you know what, I don't like that. Actually, I was thinking of this. And that's 25 degrees. Well, that's fine. Both of those are correct. So that we eliminate this confusion and all pretty much do the same thing, we talk about what it means to be a standard angle. And after this definition, from this point on, we're going to use standard angles all throughout this course. Anytime it's not a standard angle, like in some of the applications, they're going to specify northeast, northwest. We'll talk about that later. But for now, anytime we're talking about an angle, we're assuming it is a standard angle. What's a standard angle? An angle is said to be in standard position if its vertex is on the origin, right there. That's the vertex. And the initial side is always the positive x-axis. It coincides with the positive x-axis. No exception. That's always the initial, no matter what you're plotting. So we start with the positive x-axis and we define a counterclockwise motion is positive and a clockwise motion is negative. And that's how we play. So that's what a standard angle look like. As long as you start on the positive x-axis and we assume that counterclockwise motion is positive and clockwise is negative, we're set. Now if I was to go back to that example and say sketch 30, all of us will be sketching the same, 25, I'm sorry, 25. All of us will be sketching the same angle. You would assume this is the initial. It has to be. This is the terminal. And we will all be talking about the same angle. That angle right there in quadrant 1. Now, we want to practice sketching some of those. Sketch the following, and you don't need a protractor. It doesn't have to be exact, but roughly, meaning if you really look, and I'm using a color that's hard to see, don't be alarmed. This is about half, right? So if I go a full revolution around a circle, that's 360 degrees. This is half of it, 180 degrees. And this is half of this distance. That makes it 90 degrees. So this is 90, 180, 270 degrees, and 360 degrees. With the same analogy, I could say this is 0. And in case you don't know, this is 2 pi radians. One full round around the circle is 2 pi radians, or 360 degrees. This is half of it, which means it's pi. This is half of this distance, In this class, we're going to be dealing with a lot of fractions. Whenever I say half, don't think of dividing by 2. Think of multiplying. Multiply by a half, that's pi over 2. 1 pi over 2, 2 pi over 2, 3 pi over 2. So, what we get out of this is that 2 pi radians are the equivalent of 360 degrees. If I'm talking about degrees, I have to give it that symbol. If I don't, it's radians. If I divide by 2 both sides, the key to any conversion between radians and degrees is right there. There's another measuring for angle called gradient. We don't worry about that. So let me go back to this. If I am to cut this in half, this is the 45-degree line because this is 90 degrees. And since this cuts it in half, that line right there is about 45 degrees. So all what you have to do is kind of use it as a scale. 75 degrees is more than 45. All what I ask is that you sketch somewhere above 45 degrees and you tell me, look, that's 75 degrees. And you could wipe this out. Of course, you don't need it. You could use that as an imaginary line in your head. And that's good enough. I'm not going to get a protractor and go out there and measure it and see if it is or it's not. So if I wanted to sketch an angle that happened to be 385 degrees, well, I know this is positive rotation, 360 degrees. So I have to go above 360 degrees by how many? By 25 degrees more. Well, I know this is 45, so I have to stop short of that line. Again, use that just as a guideline. And you would say, this right here is my 385 degrees. And if I ask you to rotate negative 140 degrees, you would say, all right, well, that's negative 90, right? In negative rotation. And another what? Another 50. So again, 45 degrees, the imaginary line, I'm going to erase this line. That's the 45 degrees. From 90 to 140, that's 50. That's a bit more than that line. So all what I have to do is exceed that line by a bit again. It's going to look like it is on the 45. Well, that's close enough. Again, I don't measure that, but it should exceed the mid by a bit, and make sure you label it. When I say the mid, I mean the halfway mark, which is 45 degrees. Now, radians for now we're not happy with. You're going to be very happy with them once you start using them. So if I take pi over 3, and I'm thinking, well, wait a minute. What does that look like as far as radians? Well, I could convert. I could say, again, I don't mind you doing this. You could say, well, let's take that and multiply it. Anytime I want to convert, there's the star ratio. If I want radians at the bottom, that's radians, that's degrees. In the beginning, you could do this. 3 divides 18 6 times, so that's 60 degrees. You want to do that on the first test? Good for you. This is 45-degree mark, so I'm going to pass that 60 degrees. You could say that's 60 degrees right there. Now, I don't mind you even labeling that as 60 degrees. I'd rather you get used to pi over 3. But if you label it 60 degrees, it's fine with me. And if I was to say, let's label this angle, well, again, if you don't know what that is, we're going to get used to this. We could convert. We could take pretty much any angle and convert it. The ratio is right there. If I want to get rid of radians, I want radians in the denominator, and 180 degrees and pi go hand in hand. Those cancel out. 6 divides 30 degrees. So that's 150 degrees. Well, I know where 150 is. This is 90 degrees. This is 180 degrees. From 90, that's 60 past this. So a bit more than the halfway mark. Whether you tell me this is 150 degrees, or whether you tell me this is 5 pi over 6, for now, I don't mind. It's all good. Whatever works. How about 5 pi over 4? Again, if you're not familiar with that, let's convert. Pi on the denominator, degrees at the top. Those cancel out. 4 divides 180. What is that? 90. 45. And 5 times 45, that's 25. 22. 225 degrees. Well, this is 90 degrees. This is 180. This is 270. So it is definitely past the 180, but not to exceed 270. If I am at 180, how far do you go from 180? You go literally halfway through. And that would be my, either you tell me this is 225 degrees, me and you are happy, or you say that's 5 pi over 4, me and you are very happy. Now, the next set of problems, I want to convert back and forth. I want to make sure you can take any degrees, convert to radians, any radians, convert to degrees. I have 25 degrees, I want to convert to radians. If I want to get rid of degrees, I want degrees in the denominator and radians at the top. And that's going to be the zeros and the degrees cancel, the degrees cancel out. If I divide this by 5, that's 5. If I divide this by 5, 5 divides 15 3 times. You have 3 left over. And 5 divides 30 6 times. That's 5 pi over 36. If I want to convert 32 degrees, well, to radians, I want degrees in the denominator, radians at the top. The degrees cancel out and the zeros cancel out. I could divide the top by 6. 30 divided by 6 is 5. And 18 divided by 6 is 3. Negative 100 degrees, well, we're getting the hang of this, I hope. 180 degrees in the denominator. Pi at the top. The degrees cancel out. 0 cancel out. Divide by 2. That's a 5. Divide by 2. That's a 9. And 7 degrees, well, again, degrees in the denominator. Pi at the top. The degrees cancel out. It doesn't reduce, so that's 7 pi divided by 180. Which, by the way, is a very small number. And here, if I wanted to really give you the golden ratio, I would divide on my calculator. I'll divide this by pi and this by pi, and I'll get 1 radian is roughly 180 divided by pi. That's 57.3 degrees. It's roughly 57 degrees. Keep that in mind. So when I say 2 radians, that's about 144 degrees. That's a lot. Don't mix those two. Now I want to go backwards. I'm given radians. I want to convert to degrees. Well, again, the golden ratio, we already know what that is. That's pi and 180. Since I want to go to degrees, I want degrees at the top, radians at the bottom. Pi will always go with radians. 180 will go with degrees. Those cancel out. 3 divides 18 6 times 60. 2 times 60 is 120 degrees. 3 pi over 5. If I multiply by, again, I want degrees, so I want degrees at the top and pi at the bottom. Those cancel out. 5 divides 5 one time. 5 divides, we said 36, was it? 150, 180. That's going to be 3 times 36. 3 times 6, 18. 9, 108 degrees, if I'm not mistaken. 7 pi over 18, I want to convert to degrees. Again, the pi's cancel out. 18 divided 180 10 times. So that is the equivalent of 70 degrees. And if I take 1 radian, again, this is not 1 degrees, 1 radian. I want pi at the bottom and 180 degrees at the top. That would be 180 divided by pi, and that's going to be degrees. Periodic functions. Those are functions that repeat. We use those in tons of applications. The periodic function for the days of the week is 7, which means every 7 days you're back where you started. The periodic numbers of weeks per year is 52. Every 52 weeks a new year starts. The periodic numbers for months in a year is 12. Every 12 months you start over again. January comes up every 12 months. If I went to a market and you knew that I go there every 7 days or every 8, then you could predict from the period when I'm going to be there. Right? So for us, a period is 360 degrees or 2 pi. Because in a circle, whenever you rotate 360 degrees, you're back where you started. So for periodic, we talk about what's known as the famous coterminal angles. What are coterminal angles? Those are two angles that share the same initial side and the same terminal side. Meaning, if you give me an angle in standard position, if you tell me this is angle alpha, well, guess what? If I go to alpha itself and I rotate from alpha 360 degrees, I'm back where I started. Or if I go to alpha, so I'm right here, and I run 360 degrees in negative rotation from where alpha is, I'm back where I started. When somebody tells you, oh, you know, we were playing on this team, we turned this team around 360 degrees, that means they're back where they started. What they mean to say, we rotated this team 180 degrees. Instead of pointing in one direction, now we're pointing in the opposite. If you rotate 360 degrees, you're back where you started. You're doing the same thing basically. So, coterminal angles and reference angles are two things that are going to play a big role for us. Coterminal angles are in this section, reference in the next section. So, find two positive and two negative angles that are coterminal with a given standard angle. How many coterminal angles I could find? As many as I like. Give me any angle at any given time. I could add 360 to it, subtract 260 from it, or add 2 pi or subtract 2 pi. It's all good. I'm back where I started. So in this case, I have 2 pi over 3. If I start with radians, let's stick with radians. So I could add 2 pi to this. If I add 2 pi to this, what would that be? That's 2 pi over 1, right? So I could go this way actually. Or wouldn't that be the equivalent of over 3 multiplied by 3 top and bottom, 6 pi over 3? If I take 2 pi over 3 and I add 6 pi over 3, isn't that 8 pi over 3? That's coterminal. And if I add another 6, because that's another 2 pi, that will be 14 pi over 3. I could find as many positives as I like. I could add another 6, 20 pi over 3. But I only need 2 positives, so any 2 will do. And 2 negatives. The negatives, instead of adding, I would subtract. What is 2 pi over 3 minus 6 pi over 3? Well, if the denominators are the same, 2 minus 6 is negative 4, that's 1. subtract another 6, negative 10 pi over 3. That's 2. I could do more, of course. And I'm doing this with ease, not because I know trig, because I know fractions. You should do the same. 3 pi over 5. It says find two positive. It doesn't say which two. Any two will do. So I'm going to add and subtract 2 pi. But I know the drill. It's really 2 pi, but I need it to be over 5 to make this easy. So 2 pi over 1 multiplied by 5, top and bottom, that's 10 pi over 5. So the first would be add 3 plus 10, 13 pi over 5 would be coterminal. Another 10, 23 pi over 5 will do. And if I want to subtract 3 pi over 5 minus 10 pi over 5, all over 5, 3 pi minus 10 pi is negative 7 pi. And subtract another 10, that's negative 17 pi over 5. And that would be two positives, two negatives. I could find as many as I like. And if I'm looking at degrees, well, I know it's going to be a multiple of 360 degrees, right? So I could add 360 to that. That will be my first angle, 0, 7, 570. Make sure you put that symbol. And if I add another 360 to this, that will be 0, 13, 5, 8, 930 degrees. Those would be the two positives. And if I subtract 360 degrees, if I take 210 minus 360 degrees, what would that be? That would be negative 150 degrees. Take another 360 out, so they're both negative. 510 degrees. Negative. That would be my answer. So add 360 twice, subtract from 210, 360 twice. How about if I have an angle that's already negative? Well, if I know I'm going to add 360 and subtract 360. If I add 360 to that, that will be positive 160 degrees. And if I add another 360 to that, 0, 12, 3, 4, 520 degrees. Those are the positives. If I subtract 360, negative 200 minus 360, that's negative 560 degrees. And if I take 560 and add 360 to it, negative 920 degrees. So, given any angle, I could add or subtract 360 and see if I get the next. And that's how it works. I want to find coterminal angles, but I want them between 0 and 360 degrees, or 0 radians and 2 pi radians. 570 is bigger than 360. If I want to find coterminal, I'm always playing with the 360, nothing more. I subtract 360 from that. That's 210 degrees. Done. That's between 0 and 360 degrees. Negative 680, that's too big. I add 360 to that. So I'm going to subtract those because it's one positive, one negative. That's negative 325 degrees. That's still not between 0 to 360. That means within one rotation. So if I subtract this from 360, 5, that would be 35 degrees. If I'm dealing with radians, instead of adding or subtracting 260, I'll add or subtract 2 pi, minus 2 pi, right? But I know the drill. I need to make it over 5. What would be 2 pi over, multiplied by 5 top and bottom? 17 pi minus 10 pi is 7 pi over 5. That would work because, oh wait, take that back. Yeah, that's right, that's right. because 10 pi over 5 is 2 pi, and that's bigger than that. Done. What if I have negative 7 pi over 7? Well, the same thing. I want to add 2 pi to it, but I need it to be over 7 for this to make sense. Multiply by 7 top and bottom. That's 14 pi over 7. If I add those, 14 minus 5 is 9 pi over 7. That's between 0 and 2 pi, because 2 pi, if I want to make it over 7, that's 14 pi over 7. As long as this number between 0 and 14 pi over 7, it's fine, it'll work. Almost done. Last idea, extremely important for my trig and what's to come when I go back to chapter 5. Given a circle with a radius, given a circle with radius r and a central angle theta. What central angle theta means, theta on the center. So basically the vertex is on the center. That's what I should say. Central means the vertex is on the center of the circle. So right there. So if I actually take one of those circles, take that radius, this angle right here that has a vertex on the center is a central angle. Two things I'm going to talk about. The actual walking distance, if I put that on a flat length, I call that S, it's called arc length. And the area of the sector, the area that this angle encloses out of a circle, that's called the area of the sector. So, area of the sector, arc length. Those are given by two formulas. One of them, S equal the radius times theta, and the area that I shaded is 1/2 r squared times theta. What's the catch? Theta must be in radians. That's the only way this will work. In our class discussion, if you bring this, you're confused on it, I could elaborate more. And here we are. I have a few examples. So what do I know? I know that S equal r times theta and A equal 1/2 r squared theta. What's the catch? Theta must be in radians. Here I have example A, B, and C on 4. It says S denote the arc, the length of the arc length on a circle of radius r subtended by a central angle theta. A is the area of the sector. Find the missing sides or the missing quantities. Notice on A, they have S missing. S equal r times theta. What's r? R is 10. What's theta? 3 pi over 5. It's in radians. So, what's S? Divided by 2, that is 6 pi. If they gave me units, I would write it in. If they didn't, we just write it that way. You know, let's say this is in, I didn't do that, so I don't want to mess it up. Inch. So that would be in inches. And let's say this right here is in feet. This is in meters. So, and what is the area? area equal 1/2 r squared theta. Area would be 1/2. R is 10 squared. Theta is 3 pi over 5. Area would be, that's 100. 5 divides 100 20 times. 2 divides 20 10 times. That's 30 pi square inches. Any word problem, you would have to write the units at the end. Example B. I'm missing the angle and the area, but I know that S equal R times theta. What's S? In this case, S is 8. I should have put feet on it. That's okay. R is 5. That's given. What's theta? Theta is 8 over 5 radians. Done. And how about the area of the sector? Area of the sector is 1/2 r squared theta. Area of a sector is 1/2. The radius is 5, and the angle is 8/5. Area would be 25 divided by 2. That's a 4. That's 20. What would be the units for area if a side is in feet? Square feet. And what if I wanted to get to C? In C, I'm given S, 6 equal R times theta, but theta is 20 degrees. So here I have to convert. I have to go on the side and say, okay, if I want 20 degrees times pi over 180. I can't use those two formulas unless theta is in radians. That cancel out. 2 divides that 9 times. That's the equivalent of pi over 9. There it is. What would be R? 5 times 9, 54 over pi. And what are the units? Meters. And what's the area? Area of the sector would be 1/2 r squared times theta, and theta is pi over 9. Area would be, let's see what that is. That's gonna be, you know what? It's a big mess. Let's leave it like that. That's okay. And what if I wanted you to do this problem? What if I gave you the graph? And I'm saying find the area of the sector, and I'm pointing to this sector. And find S. Well, first, don't you need to convert 70 degrees to radians? Isn't that 7 pi over 18? So S equal R, R is 3, times theta. S would equal 7 pi over 6 inches. And area is 1/2 r squared times theta. This is a 9. 9 divides 2 times. So A is 7 pi over 4 square inches. And that pretty much takes care of this section.